Hello all. This lecture is about clustering, k-means clustering. In the last lecture, that is lecture 1, we saw the classification of machine learning techniques, namely supervised, unsupervised, and reinforcement learning. The clustering comes under the category of unsupervised learning. When we look at clustering techniques, they are broadly classified into hierarchical and partitional. So when we see of hierarchical clustering, it is similar to the tree construction, binary search tree or any tree construction we see in data structures. Again, hierarchical clustering is further divided into two categories, namely agglomerative and divisive clustering algorithms. In agglomerative clustering is done in a bottom-up fashion. Say, for example, an example would make it even more clear. Say, for example, I have 5 data points, and we are supposed to group the similar data points into clusters. So let's say the 5 data points are documents, and we have D1, D2, D3, D4, and D5. First, what we do is that we consider each of the single document as a single cluster, and then we start building the cluster in the bottom-up fashion. So first we'll take the D1 and D2 and we'll check whether they are similar or not. Then if they are found to be similar, they are grouped into one cluster, and then we take D3 and compare with this single cluster, pull it to this cluster if it is similar, or we'll isolate it if it's not. So similarly, we'll check with D4 and D5, and we'll go on repeatedly go on till we reach the desired number of clusters. The divisive algorithms on the other side is the reverse way around, in which all the data points, all the documents are considered as a single cluster initially, and then the dissimilar clusters are separated out, and then we based upon the dissimilarity metrics, and then we stop the clustering algorithms. That's about the hierarchical clustering. We'll see in detail about in the upcoming lectures. So today we'll see about the k-means clustering, which comes into the category of partition. We'll see first about the Euclidean distance metric. This distance metric is going to tell how similar two data points or how dissimilar two data points are. So the similarity is calculated in terms of the distance between their attributes of the data points. These attributes are nothing but the features of the data points. So since we said our data points are going to be documents, let's say the features can be words. So the words, since the distance is calculated between two dimensions. So we have two dimensions shown here, that is x coordinate and the y coordinate. A document can be represented here. We can visualize the documents to be represented by a two-dimensional vector, namely a word and its word count. So that's how we are going to calculate the. So let's say we are going to calculate the distance between two documents D1 and D2, and let's say in D1 we have 10 number of XY pairs, which are nothing but the words and the word counts. And similarly, we also have X and Y coordinates, that is word and word count pairs in D2. Now we are going to find the differences between each of the coordinates, and we are going to take the square and sum them up, and that is going to be the final distance between the two documents. That's how this distance metric is going to help us to yeah. So this is k-mean. The k-means clustering is going to use this Euclidean metric to compute the similarity between the data points. The k, we need to decide the k initially. So that's the assumption we need to make. The k is the number of clusters we are interested in. Say, for example, I have 100 documents and I'm only interested in getting 3 clusters out of it, and then I have to fix the number of fix the value of k. So this is done heuristically. Let's say let's say I build the clustering technique using k value as 3. Then when I tested the model, I found that there were polluting data points present in the cluster. So I felt like increasing the value of k. Then I can always go back and increase the value of k and do the clustering again to increase the efficiency. That is done by a trial and error way. So that is about k-means. This is the detailed step. So as we said, step 1, we have to fix the number of k clusters, and then what we need to do is that since we fix the value of k, say for example I have to put things simple. So let's say I have 5 documents in hand, and the k is 2. Then I need to pick two clusters where I fix the value of k to be 2. So now I have to randomly pull data points to either of this cluster. So I will take only one sample, that is D1, and put it into cluster 1, and I'll take D2 and put it into the cluster 2. So now I need to decide on the rest of the samples to pull in either a cluster 1 and cluster 2. So even the D2 which is already there in the cluster 2 can eventually go, there is a possibility that it can eventually go to the cluster 1 if the rest of the data points get into the cluster 2. So each time we assign a data point to the cluster, we need to compute the centroid. So the centroid coordinate, which is a representation of all the attributes or the coordinates or the parameters of the vector representation of the data point. So we need to compute centroid, and we need to compare with this centroid and the new data point that is coming into the cluster. So we need to do this, and then we'll keep on repeating this step until no data point tends to move across the clusters, and that is the point of convergence. At that point, we will stop. To make things even more clear, so we'll see an example. As we said earlier, so say for example, we have documents D1, D2, D3, and D4, and we have two attributes here. So one attribute is the word, and the other attribute is going to be the home. These are the x and y coordinates. For simplicity, let's say the document 1 has only one coordinate, but that is not the real scenario. A document will be represented by more than one pair of coordinate. For simplicity, it is being shown like that. So initially, we take the document 1 and document 2 as two clusters, the initial clusters. Since the case 2, so we have two clusters. So then the centroid of the respective clusters are going to be the data points itself, because there is only one cluster in the document. So now what we are going to do is that we are going to take the document 3, that is represented as 4 comma 3, and going to compute the equivalent distance between C1 and C2. So it is observed that the distance to the cluster 1 is 3.61 and the second cluster is 2.82. So hence the distance between the C2 and the document 3 is lesser compared to the C1. So we pull the document D3 to the C2 cluster. Now what we have to do is that since document 3 is being assigned to the document as the cluster 2, we have to recalculate the cluster data, centroid of the cluster 2. And then what we do is that we try to pull in the document 4 to either of the two clusters. So we observe that we calculate the new centroid, and then we observe that the document 4 goes to the group 2. Now what we do is that at the iteration, so we again, after pulling the document 4 to the cluster 2, we again calculate the new centroid. So even after doing this, there is a possibility that this is where the crux of the k-means algorithm lies. Even though we have grouped a document 2, document 3, and document 4 in the cluster 2, there is a possibility now that either of the data points present in the cluster 2 might shift to cluster 1. So because we're going to calculate the centroid again, and to this centroid we'll again calculate the distance between the data points, each of the data point member data points of. When we do that, this is going to be the final result. So we find that the document and 1 and 2 fall into the group of 1, that is cluster 1, and document 3 and 4 fell into the cluster of 2. So initially, remember that the document 2 was in the cluster 2, but after we added the document 4 to the cluster 1, the cluster 2 had to shift itself to the cluster 1, because the centroid of the cluster 2 was farther than compared to the document 1 cluster. So that's the crux of k-means algorithms. And after this, there is no shift between the document data points across the clusters, so we can stop. Yeah, so that's about the k-means clustering algorithm. So the weakness is only about so because we are making assumptions, there are more assumptions to it. So that makes k-means weaker. The number of k we decide. So so in the example we gave, it so the simple example, but when we actually do the k-mean clustering for a large number of data, it is going to be even worse, because if we make some mistake in fixing the number of k, the entire k-mean clustering training goes bad. So that is the initial, that is one of the weakness. And then the randomly assigning points to the cluster. So in the example what we discussed, we pulled in D1 initially to cluster 1 and D2 initially to the cluster 2. So this itself, because the rest of the clusters were pulled to the C2 cluster based upon its distance, the initially decided pulled in data point. This might give you a bad cluster. So it might also give a good cluster, but in case if D2 was a bad cluster, then it might, the entire cluster can go bad. So that these are the two weaknesses that prevail in k-means clustering. The efficiency of k-means clustering, so no matter how many shifts the data points can go between, take between the clusters, or we even recompute the centroid each and every time we move in or move out the data point from the cluster. So it is going to only throw you a big O of n. So the worst time complexity is going to be big O of n, and where here it is tkn, where t is going to be the number of iterations we take to shift the number of to shift the data points across the clusters, and n is going to be the number of objects, and k is the number of clusters we are interested in.